Hey, hello, I'm Akhil. And now in this video, we will be seeing the network bandwidth parameters. In the first part of the experiment, we will be seeing the bandwidth throughput in both TCP and the UDP using a tool called iperf, and how the bandwidth affects the throughput, and also we will see how the window size also affects the throughput of the network. To see all these things, first we have to go to our data labs. Now I'm already in my data labs. Uh, since I've already created an experiment, which is this, and this is already been swapped in. So we can see the NS file which I've used for creating this experiment. In this, I've created two nodes, node A and node B, and I've created a duplex link with a bandwidth of 1 megabits per second and a round trip and a delay and a round trip time of 25 milliseconds, which I've mentioned it as 12.5 since it's a duplex link. And the operating system we are going to use in this experiment is Ubuntu 16.04. Now we will see the visualization. Here you can see that we have created two nodes. This is node A and node B with RTT of 12.5 milliseconds. Now, to start the experiment, we have to go into the terminals. Go to terminal. We are in the terminals. SSH into the data labs. SSH. Enter your username and password. And the password. Now we are inside the data labs. Do it the same for over here. SSH yes, 4280 at enter the password. And now you are inside this week. Now we have to SSH into the nodes. So SSH and see the qualified name of the node, which is this. Oh, sorry. This is node A. Oh, I think I've missed N over here. And enter. Now you can see that you are inside the node A. We'll do this for the node B as such. Instead of node A, we'll type node B and we missed an N. Now you can see that we are inside the node B. So now to check or verify the round trip delay time, we'll ping from the node A to node B and see what is the round trip delay time. So for that, the command is ping. Let's see, 3 node. You can see that the round trip delay time is 24 over here, which is here. And we have also mentioned it around to be 25. So approximately this works. The round trip delay time is working perfectly. Now, now we are going to perform the iperf tool, which will give the network our bandwidth or throughput parameters for this network. For that, so now we are going to perform iperf in UDP mode. For that, we have to type the command iperf hyphen yes hyphen u. This will create a UDP iperf server at node A. See, you can see that the server has been created and the buffer size is 208 kilobytes. Now we'll make node B as the client. For that, the command is same. No, first we have to okay and iperf C the destination, which is node A hyphen U, because this is an UDP. Now you can see that there is the uh, uh, throughput has been calculated 973 kilobits per second. This is the throughput for 1 Mbps of bandwidth in UDP. Now we'll perform the same experiment in TCP as well. So I'll just get out of this. And now to perform iperf in TCP mode, we have to give this command. I'm considering the node A as the server, which is dash S. Oh, sorry, I have to give the path iperf hyphen S. Oh, sorry, hyphen S. Now you can see that we are running the iperf in the TCP port, which has a window size of 85.3 kilobytes. And now we'll do the same thing for the client as well. iperf hyphen C node A. You can see that the process has been started and it will take a while to get completed to get the bandwidth and all. You can see that the bandwidth of the network which we created with 1 Mbps of link speed in TCP mode is 933 kilobits per second. Now, from the both results which we got, we can say that the TCP is slightly less accurate than the UDP because for the UDP we got 973 kilobits per second, and for the TCP we're getting 933 kilobits per second. Now we are going to perform the same experiment with the different link speeds. For that, we have to let's terminate this. Go to our ISO editor lab4 and modify traffic shaping. Now we can see that the bandwidth is 1 Mbps over here. Now we are going to make it 10 Mbps. 3, 3. You can see that the bandwidth has been changed, and now we are going to perform this experiment again. Now we are going to perform this in the UDP mode. S-U, enter. You can see that the buffer size is 208, which is default buffer size. C node A hyphen U because it is in UDP. Now we have to wait for a second because we'll get the analysis in. And you can see that the buffer size for the UDP here is also 208 kilobytes, which is the default one. Now you can see that now here you can see that the UDP's bandwidth is 1.05 megabits per second, which is very much lower than the bandwidth which we are providing for the link, which is 10 Mbps. This is because iPerf does not allow the UDP clients to get the bandwidth of more than 1 Mbps. So, okay, now for the next step, we will be doing the iPerf for 10 megabits per second in TCP mode. For that, I have to go just remove the U, and now you can see the TCP window size is 85.3, and remove the U over here as well. And we have to wait for just a second to complete the transfer and get the analytics. When I did previously the same thing, I got a throughput of 9.39 megabits per second in the server side. I think this may take a few moments. That's why I'm showing you this result, which I did it previously to check if it is working or not. And now, as a next part of the experiment, we have to modify the traffic shaping and change the bandwidth to 100 kb, 100 megabits per second. I'll change it over here. You can see that it has bandwidth has been changed, and it's taking forever. So I think I will terminate this and run again. Yes. Okay. Now you can see that we get a throughput of 93 megabits per second for 100 mbps throughput bandwidth. Now, so the readings were collected in a table and were something like this. We calculated all these things and we got the values such as for TCP we got these values and for the UDP we got these values. And when we plot a graph, we see that there is for the default window size of 85 kilobytes per second. You can see that there is not much difference between the performance of TCP and UDP, but the UDP performs a little better than that UDP. The UDP has a throughput of 95.7 at 100 Mbps of speed of bandwidth link speed, and TCP has a throughput of 93 at 100 Mbps of speed. And now moving on to the next part of the experiment, we will be changing the window sizes of the experiment of the network topology. For that, the command would be same thing, but we have to now we are in node A just hyphen W 64K. Here you can see that for a 64 kilobytes window size, we got a throughput of 27.9 megabits per second. And during the meanwhile, when it was loading, I did a command to find out the throughput when the window size is 128 kilobytes. For that, we got a throughput of 53.1 megabits per second when the link bandwidth is 100 megabits per second. Now we'll perform the same experiment for a window size of 256 kilobytes. You can see that we got a throughput of 84.4 megabits per second. And now we go to the data labs and we're going to modify the traffic network shapings. Now we are going to make this link bandwidth to 10 Mbps. So that would be 1, 2, 3, 4. Yeah, save and execute. You can see that it has been changed. Now we go to here and this has been created for a window size of 64 kilobytes. We can see that we got for 64 kilobytes, we got a throughput of 9.39 megabits per second. Now we'll try for 128 kilobytes. Now we can see for 940 megabits per second, and now we'll see it for 256 kilobytes. You can see that the same thing, and we got the similar results for this as well. For 10 we got 9.41 and 128 we got same thing, and the 10 in the 64 also we got the same throughput. This is because this is the bottleneck of the link, we guess. So we are able to get only 9.4 megabits per second at different window sizes. And when we plot a graph for this, it looks something like this. And from this, we can infer that the throughput increases as the window size increases. And for the next part of the experiment, we were told to calculate the supposed to calculate the window size. The window size formula is given by the link speed and the latency divided by 8, and the unit of this is bytes. And when we calculated this for an 100 Mbps link and 25 milliseconds latency, the critical window size would be 312 kilobytes. So now when we run this uh, experiment with the a window size of 312 kilobytes, we will have to see what is the throughput we get. Now you can see that we're getting a throughput of 84.3 megabits per second. But theoretically, we should for this window size we should get a throughput of 100 megabits per second. The problems maybe uh, the throughput to be less is the latency in receiving the acknowledgement increases, and when the latency is high, the sender is idle, and this affects the throughput. This may be one of the reasons, and the other reasons may be because of the network overheads, which affects the performance of the throughput and reduces the performance of real throughput versus a theoretical throughput. And additionally, there will be certain loss of data packets because of the data congestion, and that in TCP we have to get the acknowledgements back and forth. So these will be the reasons of less throughput than the theoretical throughput. Yeah, now we will see the second part of the experiment.
So this is the part 2 of the lab experiment of E542, that is network bandwidth measurement. So this is the second part that I'll be highlighting, that is the gigabit links. So it is almost similar to what we have done in bandwidth delay product. Only thing is then some changes has to be made in our NS file. So I'll show you what changes has to be made. So you see, since we are dealing with gigabit LAN, we made changes over here in LAN 0. As per the requirement, we need to set return experiment with the gigabit LAN. So we are making use of this one. We made changes over here. Also, we set the operating system of node A and node B to Ubuntu 1604 std. Then we log into our data file. So I've already swapped in the experiment, given that it takes up quite a significant amount of time. So I have usually swapped in. The NSS file reflects what we have done over here. If you see, we have set as 1 GB of gigabit LAN, which is as required over here. So we have done this regarding it, and also the necessary visualization part is over here. You can see it is reflected on this part. You can see over here. So I'll just zoom in a bit. Yeah, you can see that it's 1 gigabyte. Yeah, so now we start with our ISR. We need to use Puppy to log in to our account and conduct our experiment. So we use two first part is we begin with SSH into a node, respective node A and node B. So we use this one. This is we SSH into node A and node B respectively. So you can see over here that it is node A and this is node B. It's up to us to determine which is the server and the client. So I'm choosing node A as my server and node B as my client. So the first part of the experiment is we need to determine the average RTT between the computers. So what I can simply do is, like from the server side, I can just ping node B. So we can wait for certain amount of packets being transmitted before I use Control C to determine the RTT. So you see it's 0.117. After the 13th packet transmission we get 0.117, which is roughly to what we have mentioned in our laboratory in PPT, that we are getting 0.118 and we are getting 0.117. So roughly the same amount of RTT, average RTT that we look at when you ping from node A to node B. It matches to what is required or what we have presented in our presentation PPT at 0.88. So the average routed RAM for the gigabit link is 0.118 in our experiment. Now we come to the second part of this experiment, that is when the maximum bandwidth delivered product and use IPRF in UDP mode. So first we use to access it using the UDP mode, we need to do this. So first we need to go to the path where the IPRF tool is stored on data lab. So this is what the path is. We copy paste it into this one. So from here, and we set this as a server. Since we are using the UDP mode, we use -u. This -u is for UDP, signifies the UDP mode in IPRF tool. So and we set the bandwidth as 1 gigabyte. Similarly, this is our client, and we select the server as node A, and we select 1 gigabyte. So yeah, we'll wait for this to happen. Packets to be transmitted. So we see that this is what we get for our this one 957. You see is a bandwidth that we get in UDP mode. This is what we have portrayed over here. You see the bandwidth mode is 957, and this is what we get over here. 957 megabits per second is what the bandwidth in UDP mode is. Now we need to find the throughput in TCP mode. So we do the same thing in different. So we Control C, and we need to find in the TCP mode. So we do the same thing. Only thing is we need to remove the -s. The same over here. It's so sorry, this is my sorry for this one. I put minus s over here, and this is minus c node here. I'm sorry. So this is a mistake I made. By mistake I put minus a. Now I change it to minus c. This is what it is all about. So we see that the throughput that we get over here is this one, 943 megabits per second. Server side, if you see, it's 941, not a major difference, and we report the numbers 941 on the server side, and this is what we have obtained over here, 943. If you see, throughput of TCP mode is 943 megabits per second, so that's what we get it. So if you see the same 943 over here is the throughput that we get on client side. So we just close the connection. So that's the requirement that if you leave the send and receive window at the default values, will this link perform well? Well, I guess this performs well. You know, the TCP throughput that we have got, the TCP throughput that we got was 943, and which a default send window. So I think the gigabit LAN has performed decently well. So this is what our experiment had shown. In the second case, we need to scale the send and receive windows to see the effect. So we start scaling the window sizes. So these are the values that we have taken. So we'll be measuring around this 5, 25, 50, 75, 100, 550 and 101, 200. So I'll be measuring around these values. So I set up my initial thing. So it's minus w. So at initially kilobyte I use this. This minus w symbolizes the window size. So this minus 20, minus 5 is the window that I'm setting at kilobytes, and this window size in kilobytes. So I've given 5 KB as an initial value. So first we observe that it's at 154. So secondly, again we do it. Again we do it at 25 kilobyte. Then we again choose some values of 50 and 75. We see this. We choose the value 100, 550 and 200 over here. You see that it's 940. We again go for higher value, that is 150. We choose for 150. We see that 941. These values are almost the same at 941, 941. So I'm getting this almost the same value as we increase the window size. So to confirm ourselves further, I go for 200 kilobyte of window size. it's 941. So this reflects what we have achieved over here. And you see, if you see the graph, it will increase, decrease, and then at one particular point it becomes constant. You see, so after this it becomes very constant, the values. So that's what we see a marginal difference into about how we go from here. So these particular values has become constant at 941. These value signifies a constant value. So as you see, we increase the window size from 5 kilobyte to 200 kilobytes, and you observe that the throughput increased when the window size increases, and the maximum throughput is achieved when the window size reaches the bandwidth delay product. It makes sense, that controlling. You see, does it make sense? So yeah, I believe it makes sense. It makes sense that if we change the window sizes, there's a corresponding effect on the throughput. If we keep the window size to very low value, we have already seen that the throughput of the gigabit link is very low. It only increases when the window size is equal to the bandwidth delay product. So this answers our part. Now to check whether therefore that for the lower values the gigabit link cannot perform well with small window size. So it's better that we increasing increasing window size, the throughput is relatively better. Now coming to this part, with 1 millisecond of or 5 millisecond of gigabit link, we need a window size of up to 625 kb. The calculation, we have put the calculation over here. A gigabit stream link with 1 milliseconds or 5 milliseconds of delay, we need a window size of 625 kb to get the maximum throughput, I think, which is achievable. So I guess this is achievable if we keep it with a delay of 1 millisecond, 5 milliseconds. Now we need to need to ask ourselves whether 1 gigabyte of DSL connection would be more significant. Well, for 1 gigabyte of DSL, we can get a better throughput. Window size also increases. From the previous step itself, we can see, and from the result that we have secured of the scaling of window sizes, we see that 1 gigabit of DSL will have some pronounced effect on window size. So changing the window size can control the throughput. Hence, 1 GB of DSL with accessing only to window size is acceptable in our experiment.
Hi, this is Shen Yu, and this is part 2 about its secret copy. And I'm swapping the experiment with 2 node and 100 megabytes bandwidth link and some delay, and I change the delay to 0. Okay, now it's 0. And let's get into the node. Okay, we have access to node A and node B. Now we want to measure the delay between two nodes. We will use the pin. We can see the average here is on 0.558, and bandwidth delay will be so 100 megabytes. So it's sorry, and the delay is millisecond, so it will around 58k bits, the bandwidth delay product. Okay, now we need to mountain the temporary local file system to each node. We will do this by node A has the ownership of node B, so we need to give the ownership to of node B to node A. Okay, great. Now we need to create a 200 megabyte file in node A. Mountain. Okay, so this command will fill 201 megabyte large random file to the data bin. Okay, let's change to need a sudo. So we now have a 200 megabyte data in here, data bin, and then now we need to copy it to from node A to node B. Okay, now so node A had node B's ownership and go transmission the file. Okay. You can see here's the throughput. It's in bytes, so time it to 8, it's megabits. So it's almost like 84. Yeah, 84 megabits. It's a throughput. Now we increase the delay. First we give it a small delay, like 12. Let's do it again. Yeah, you can see we still get almost maximum throughput. Let's give a bigger delay, like 25. Okay, let's try again. Okay, it's 15 millisecond wrong way, but it still gets a full through up. Let's try bigger. Okay, now you can see we get a decreased throughput. Oh, it's not. The reason for that, the increased delay and not decreased throughput is because the default maximum window size is pretty big, so the TCP will dramatically change the window size. So when the delay is increased, TCP will increase the window size too. So the throughput is still same. We can check the default. Sorry. So here we can see the default maximum window size is pretty big. We can so what that means is if you have a huge delay and your throughput is small, you can change the maximum window size. So a bigger window size, so the throughput will be bigger too. Yeah, we change the send buffer, the maximum window size. We change it. We decrease the default maximum send buffer, so the speed go really down. We change it back. You can see the speed is get little up because we changed the maximum window size a little bit bigger, so the speed is go up a little bit too slow. That's what I mean. So if you have a huge delay, you can by changing the kernel maximum window size to improve the performance. And I'm going to change it back to the default size, so it's 6. Okay. And now we get the full through. Yeah, I think it's almost full through out. Okay. So now we change the delay to 0 and increase the loss ratio. It's 0.1%. Okay, let's check again. So we still have the almost maximum throughput. Increase it a bit. still good. Let's add more delay. Sorry, loss. It's 1%. Let's check the result. Still not bad because of the high maximum window size. It's still not decrease the throughput. At 2%. Now we can notice some decrease with the increase of the loss rate ratio. So first keep decreasing 4%. %. You can notice the decrease is not linear. It kind of extremely change with the variance of loss level. I think the reason of that because every time a packet is lost, so it's need to be retransmission again, which is cost a lot of time. That's why it's changed extremely with the loss level. You can see when the loss ratio is 5%, it's almost half of the throughput. Okay. The limitation of the SCP, I think it's like because the SCP is run over SS protocol, so it is limited by the fact that there is a layered window of SH that runs over TCP receive window. So because TCP window size has a increased factor, but SH doesn't have that one, so as the bandwidth increase, the throughput cannot exceed the window size of SSH. That's the limitation. And for the delay and the loss between Los Angeles and Switzerland, I can measure it by ping to the Google homepage of Switzerland. Here's the IP address. Okay, it's sorry. So it's around 16.6 millisecond, and the loss rate is 0%. So I think it's not too bad for downloading. If the colleague asks me for help, I will change the maximum window size for him to improve the download performance. Thank you. I think that's all for the lab 4 part 2.